So by now we're quite familiar with the notation limit as x approaches c of f of x for a regular function, and we have also seen what we mean by the limit as t approaching c of a parametric curve. It just means that we're looking at the two limits separately for the x and the y coordinate. So far so good, but what about polar curves? Remember, these polar curves are curves which are defined in terms of polar coordinates and are best suited for curves that have some kind of rotating pattern around the pole. Well, one thing we could do is simply ask what happens to r as theta approaches some number c. That is definitely a reasonable question to ask. Unfortunately, it's a pretty boring question. It doesn't really give us a lot of information at this stage. Now, later on, if you go more into polar curves, into the study of polar curves, you may see some more uses of this idea, but for now, not really interesting. Instead, what we would like to do is still focus on the basic question we've been dealing with right now, namely, what happens to x and y as theta approaches c? Now, that's an interesting question. And of course we can do that because we know that polar curves have a parametric version. So if we change a polar curve to parametric form, now we're back to what we were saying a minute ago about limits of parametric curves. So let's see how that works through an example. I'm going to show you an example that highlights a little bit some of the similarities and the differences between what happens with parametric curves and what happens with polar curves. So the example I'm going to give you is the curve r equal cosine theta over theta minus pi. If you have a calculator, and I'm sure you do, you may want to just start having a look at what this graph looks like, or you may want to wait and see first of all what this curve has in store for us from the limits point of view, and then see how that is reflected in the graph. So one thing we can do is, first of all, notice that the only interesting value for which a limit may be worth computing is for theta equal pi, where the denominator becomes 0. And as I said, yeah, we could look at what is the limit as theta approaches pi of this function. Of course, we're going to end up with two different values. If we approach pi from the left, we end up with a -1 on top, with a 0 or very small negative values on the bottom, and so that goes to positive infinity. And similarly, if we approach pi from the right-hand side, we get the same thing, but with the negative in front of the infinity, so r goes to negative infinity. So these two limits tell us that as theta is approaching pi, r is going to infinity. So what? What does that mean? Does the function have a horizontal asymptote, a vertical asymptote, an oblique asymptote? Is it going out in a spiral? What's happening? We don't really have a clue. So what we need to do is actually use the parametric version. So let's do that. You may remember, I hope you do, that in order to go from a polar function to its parametric form, we multiply the formula for r by cosine theta to get the x-coordinate and by sine theta to get the y-coordinate. And if you do that, you end up with these two formulas. So this is the parametric form of our polar curve. Now, in order to facilitate what we're going to be doing later, I'm going to change the second formula a little bit. I'm going to write the right-hand side as sine of 2 theta over 2 theta minus pi. Remember that sine theta cosine theta is a half of sine of 2 theta, so I'm changing it in that form, and you'll see in a minute why. So, first of all, let's find out what happens to the x-coordinate. As x is approaching pi from the left of now the formula cosine squared of theta over theta minus pi, the top now is approaching 1 because it's being squared, and the bottom is still approaching 0 with negative values. So altogether, this formula is approaching negative infinity. Similarly, if we let theta approach pi from the positive side, we can use the same kind of argument and check that x is approaching positive infinity as theta is approaching pi from the right-hand side. So we know that x is becoming large. Now what happens to y? Well, let's look at y. As far as the y-coordinate, we're looking at the limit as theta approaches pi of sine of 2 theta over 2 times theta minus pi. But we know that the sine function is periodic with period 2 pi. So that means that if we add or subtract 2 pi from the argument of sine, the function does not change. So what we're going to do is we're going to write the top as sine of 2 theta minus 2 pi. Now notice that we have the same thing inside the sine and in the bottom. And notice also that theta is going to pi, which means that that's the same thing as saying that 2 theta minus 2 pi is approaching 0. And now look what we have now. We have a limit of the form limit as something goes to 0 of sine of something divided by that same something. Well, this is the fundamental trig limit, and we know that that is equal to 1. All right, so what have we found out? We found out that as theta is approaching pi from the left, the curve is approaching somewhere that has an x-coordinate of -infinity and a y-coordinate of 1. Well, that clearly indicates a left horizontal asymptote. And similarly, if we look on the right-hand side, then we see that x is approaching +infinity and y is approaching 1, and that indicates a right horizontal asymptote. So now, finally, by looking at the parametric version of the curve, we know exactly what is happening at that interesting value of theta equal pi. But this is not the end of the story. There is another interesting thing that we should be looking at with this polar curve. What is it? Well, what if theta goes to infinity? What's happening as theta goes to infinity? We know that when the independent variable goes to infinity, some interesting things can happen. Well, what happens now? Well, we're still going to be looking at the parametric version of the curve, and we're going to compute the limit as theta goes to infinity of the x-coordinate, so that's cosine squared theta over theta minus y, and that ends up being equal to 0. And in fact, that's the same as for the y-coordinate. So both the x and the y-coordinate are going to 0 as theta is approaching infinity. Does that mean that we have a single point hole? That's what it may look like. We're approaching something where the curve doesn't exist at theta equal infinity, but there is a point. Is that a single point hole? Well, let's have a look at the graph. The graph looks like this. That doesn't look like a single point hole. In fact, what happens is that if we compute the value of r for any value of theta of the form pi over 2 plus k pi, we always get an r value of 0, which means that this curve in fact does go through 0, 0 through the pole, and it does so infinitely many times. So this is definitely not a single point hole. What is it? Well, you're going to study this probably in some other course later on in your later years, but it's something that in mathematics sometimes is called an attractor. Notice that things happen differently in polar curves than the way they happen in parametric or regular Cartesian formulae. So don't always expect the trite result of some limits, but always think about what information the limits are providing you, and then use that information accurately and correctly to make conclusions about the graphical nature of the features you're looking at. And so this is basically the main differences that you're going to see with polar curves. Now it's just a matter for you to practice on many of these and gain as much experience as you can.